Welcome to Empowered Learning. This is the third video in the video series for finding derivatives of functions by using differentiation rules. So this last video I wanted to record because the part 2 video was getting a little long, and I knew that this example is a little bit involved, so I wanted to just record it for its own in its own video. So this is an example of a spring mass system. And what we have here is essentially a weight that is on some kind of elastic band, and that's hanging on a hook. And so since I'm not that great of an artist, this is about the best I can do with that. But the idea here is that we want to have the weight hanging on the hook. We pull it down. So let's say we'll pull it down and hold it, and then afterwards we'll let it go. And then this weight would just kind of bounce back and forth, or up and down rather. So that's kind of the idea here. And we're tracking the position of this particular mass or weight. We're just going to call it a mass here, since that's what's in the problem. For this particular mass, we're tracking its position based upon time by this particular function here. Okay. And so we are assuming in this case that t is going to be greater than or equal to 0, that the position is going to be measured in centimeters, and I haven't put this here, but I'm going to go ahead and do it now. T is going to be in what we call milliseconds. Okay, so we're just going to assume that. All right, so we're going to be asked a series of questions based upon this particular model that we have. And what we're going to be working with for the most part is just this function here. Okay. So if we go to our first question, we want to find out what is going to be the velocity and acceleration equations of this particular function at mass, of the mass at time t. Well, first thing that we know here is that if this is a position function, okay, so if s of t is a position function, then we know that v of t is going to be the velocity function, and the velocity function is going to be the first derivative of our position function. We also know that our second derivative of our position function is going to be the acceleration function. So we have this. We also know acceleration. That's going to be the second derivative. So essentially all we need to find here is the first derivative and second derivative of the given function that we have. So here we'll find the first derivative first. And of course we ignore the 2. And we know that the derivative of cosine is minus sine. So this will just end up being a minus 2 sine of t plus, ignore the 3, and then take the derivative of sine, which is cosine. To find the acceleration, we need to find the second derivative of our position function, or the first derivative of the velocity function, which is essentially we take the derivative of the derivative. So we ignore the minus 2, and we know that the derivative of sine is cosine, and plus, ignore the 3, the derivative of cosine is a minus sine, so we'll replace this plus with a minus, and do sine t. So now we have our velocity and acceleration equations to try to describe the property of this particular system here as it vibrates this mass as it bounces up and down. Okay, so we're going to go ahead and move on to our second example here. So for our second example, we're asked, when does our mass pass through the equilibrium of our system for the first time? And the key phrase there being the first time. So just as a reminder to you, we have our position function being 2 cosine t plus 3 sine t. Okay, and so we want to know when the mass passes through the equilibrium for the first time. So when our mass passes through equilibrium, the position of that mass at that time will be 0. So essentially what this is asking is, tell me when the position is equal to 0. Okay, but notice that we're asking when is position of the mass going to be equal to 0 for the first time. Okay, and also notice here that values of t are assumed to be greater than or equal to 0. So we essentially just need to set this function here equal to 0 and then solve. So we will go ahead and do that. So s of t equaling 0 means that 2 cosine of t plus 3 sine of t is equal to 0. And so to solve this, we just need to kind of algebraically manipulate what's going on here. What I will do is just go ahead and subtract both sides by 3 sine t. So this will be 2 cosine of t equals minus 3 sine of t. And from that, I know here that sine divided by cosine will be tangent, or that cosine divided by sine will be cotangent. So you can choose which one you want to do. Personally, I would rather deal with tangent versus cotangent. So what I'm going to do here is divide both sides here by cosine. Okay. And also divide both sides by -3. So if we do that, then what we end up with is a -2/3 is equal to, that reduces to 1, that reduces to 1, sine over cosine, which is tangent t. Okay. So now at this point, again, we're asked, when does this mass pass through the equilibrium for the first time? And so remember here that we are considering values of t that are greater than or equal to 0. Now, when most people look at this problem, they'll say, all right, we just need to solve for t, and to do that, we need to do the arctan or tangent inverse, right? So they will do this. So if we did that, I want to do this in a different color here. So if we did that, then we would just say t is equal to tan inverse of -2/3. All right, so if we actually use our calculator here to figure out what this is going to be, and we're going to make sure that our calculator mode here is in radians, because we're dealing with real number values here, not degrees, because time is not measured in degrees, so that's why we have to do it in radians. So here I would have second and then tangent inverse. Oh, sorry, let me get out of this right quick. So I need to get out of that and just get here. So this would be tangent inverse of -2 divided by 3. And if you notice, the answer that we get is negative. Okay. Now that's a problem, because what we're saying is the first time the mass goes through the equilibrium for times being t greater than or equal to 0 is a negative value. So if you think about that for a second, what you're actually seeing is us abusing the tangent inverse or the arctangent function, because we don't understand where it is this particular function is actually talking about in terms of time. Okay, so what we actually have to do is figure out, based upon the restrictions that we have from a angle perspective, what quadrant is angle T in. Even though we're looking at T as time and time is going to be measured in radians, we have to think about, all right, well, what quadrant or quadrants is tangent of an angle negative in. Okay, so we're going to remove the calculator here now, and let's talk about that for a second. So, because if we think about tangent in terms of quadrants here, and I'm going to switch colors again. So here we know that tangent is the ratio of sine over cosine, which is in terms of points on the unit circle. This is y coordinate on the unit circle divided by x coordinate on the unit circle. And if we're looking at a unit circle here, we know points here have both x and y being positive. Points down here, x is positive, y is negative. Here, x is negative, y is positive. And here, both of these are negative. So if we're looking at a particular point on the unit circle, if tangent is going to be negative, then that means either y is positive and x is negative, or y is negative, x is positive. So what that tells us here is that it's either going to be in quadrant 2 or quadrant 4. Okay. Now, the answer to knowing what quadrant it's supposed to be in is it is going to be in quadrant 2, and here is why. Okay. If we think about the tangent inverse function, I'm just going to write it like this, which is also known as arctan. Notice that the graph of arctangent looks like this. We have these horizontal asymptotes at y equals pi over 2, y equals negative pi over 2. And our actual graph here looks like this. Okay. The point I want to make here is that if you're using the arctangent function here, you can only use values in it in between negative pi over 2 and pi over 2. Okay. Now, to put this in terms of what we're actually doing here, remember this is an angle. Okay. So I'm going to rename these variables here. So here what we actually have is time right here. And what you have here is a ratio of position. And so I'll just call this y in general. Okay. But it's actually a ratio of position. And so here, this would be arctan of y, which again is going to be a ratio of position. So what that means here is that you're looking at this in terms of time. Notice that from here to here, this is the equivalent of quadrant 4, because negatively speaking, going from here, from the positive x-axis to the negative y-axis is quadrant 4. And going from the positive x-axis to the positive y-axis is quadrant 1. So this is quadrant 1. This is quadrant 4. So this portion of this particular function here is in quadrant 4. What you see here is in quadrant 1. And I need for tangent, if I went ahead and said tangent of t, I need this to be negative here. So notice that it can't be quadrant 4 because time is negative in quadrant 4. That's the point that I'm trying to get at. So the next quadrant that we have where time is positive and it meets this condition here is in quadrant 2. So our angle here, the terminal side of our angle, is actually going to be in quadrant 2. And what you're going to see here, this angle is representing that time. Okay. Now, if this doesn't make sense, I'll draw it another way. Okay, so I'll scroll down here. If we just look at this in terms of a tangent function, we know tangent has a fundamental period length of pi units. And so its fundamental period is in between negative pi over 2 and pi over 2. So if I look at this as t is equal to negative pi over 2, t is equal to positive pi over 2 here, then our graph looks like this. Okay. Now, we know we have, we know that this function is periodic, so that means I could draw another period here. And let's say this is where the next vertical asymptote is for tangent, and that's going to be t is equal to positive 3 pi over 2. Okay. So if that's the case, then of course right here, that will be the next place where tangent is 0 at, and we repeat the process. Okay. Now, because we know that our values of t, or our time here, has to be greater than or equal to 0, what that tells me is that I can get rid of all of this. Okay, I get rid of this side of my graph. Now, just to, and I'm going to draw this back here just to be clear here. What we actually found when we had that negative value is we found what x was here when your y value was negative 2/3. Okay, so we found this actual point on the graph of tangent. But notice here, time has to be greater than or equal to 0, so this point is not one that I actually want, based upon how my problem was defined, or how the system was defined. So this is why we are getting rid of all of this. Okay, so we're starting here when our function tangent of t is going to be greater than or equal to 0. All right, so now that we have that, notice that the first time with, if we have tangent of t equaling negative 2/3 here, first time that happens, if we keep on looking here, is right here. And so this is the actual t value. And I know I had x over here, but that should have actually been a t over there. But this is the first t value where t is greater than or equal to 0, where tangent can be negative. And so this is the time that we're looking for. If you notice, this time here is in between pi over 2 and pi, which if we want to put that numbers wise, of course, pi over 2 is going to be about 1.57, and pi is going to be about 3.14. So since we said that we were doing things in milliseconds here, this is going to be, this time is going to be between 1.57 and 3.14 milliseconds. Okay. And so to be able to find this, we have to use our tangent inverse function properly, or arctan function properly here. So since this is in quadrant 2, t is going to be pi minus tangent inverse of positive 2 over 3. Okay. Now, why is that? Well, here again, remember, we are in quadrant 2. If I go back up here and talk about quadrant 2, notice that my angle here now is going to be a positive angle, and there is this is pi here. I'm going to have some reference angle, okay? And this reference angle that's here, I'm going to draw it in a different color. This reference angle here, this is what the tan inverse of positive 2 over 3 is, okay? And notice that here there is a corresponding angle in quadrant 1. It's kind of parallel to that here. In other words, the point that's here and the point that's here, both of these points that the terminal sides of the angles go through will have the same y value here. But notice that in quadrant 1, tangent should be positive because it's going to be a ratio of y to x. Okay. And also notice that tangent inverse is only defined in quadrants 4 and in quadrant 1. So if I put positive values in a tangent inverse function, it's only going to spit out angles that are going to be in quadrant 1. If I put in negative numbers or negative values into a tangent inverse function, it's going to spit out angles that are negative. Okay? So to make all that work here, I know that this has to end up being t is equal to pi minus tangent inverse of positive 2 over 3. Now, last thing I'm going to say on that, and I'm going to move down a little bit more so I can kind of draw what's going on here, is remember that we have terminal side in quadrant 2. Okay. There is corresponding right triangle, and remember that this is a reference angle. Okay. And whenever we talk about a reference angle, it is an angle that is defined in between the x-axis and the terminal side, and it is always assumed to be a positive angle, meaning that it's an angle that's going to spin counterclockwise. And in this case, since we're dealing with a tangent inverse function, it has to be in quadrant 1. So what that means for us here is that to get our reference angle, we just wanted to look at this as, I'm going to erase this for now. If I wanted to look at this as t, which is going to be my angle, is going to be pi minus the reference angle. This reference angle here could actually be translated in this particular quadrant as well, because remember, even though the angle itself in this particular case is in quadrant 2, we translated the definition of it is an angle in between the x-axis and the terminal side, and is always is assumed to be an angle that's interpreted positively, okay, or in standard position. And so in this case, that would actually have to be something that's in quadrant 1, because we're dealing with a tangent inverse function. And so from here, we see that the ratio of tangent of something in a quadrant where this angle has to be in standard position, or tangent has to be positive, we know tangent is going to be opposite of angle over adjacent of angle. And so you see here that if we want to find out what alpha is, it is just going to be tan inverse of 2 over 3. Okay. So For all those reasons, that's why here we would actually have to find that first time by doing what you see here. And so that's why what we have here would be incorrect, and why we would need to rewrite it accordingly. All right, so now what this means for us here is that t is just going to be pi minus tan inverse of 2 over 3. And now we'll bring back in a calculator here and we'll calculate that. So this will be pi minus tangent inverse of 2 divided by 3. And here you see we get a sensible number. And so this number, we're just going to round it roughly about 2.55 milliseconds. Okay. So this would be 2.55 milliseconds. And notice from what we talked about earlier, we expected that number to be in between 1.57 and 3.14. And we see that 2.55 is in between those two numbers. So what we came up with actually makes sense. Okay. All right, so our next question in this example is asking us, how far from the equilibrium position does our mass travel? Okay. So if we think about that for a second, we know that if our mass is bouncing up and down, up and down, up and down, and let's say this is equilibrium here. As the mass is bouncing up and down, when it gets to these extremes here and here, there's going to be a moment where the mass, just for an instant, is going to stop moving before it turns around and goes in the other direction. Or it turns around and goes this way. And same deal here. It is going to stop momentarily before it tries to go back down. Now, at the instance to where the velocity just kind of stops moving, it's not increasing, it's not decreasing. At that moment, the rate of change of how it's moving is going to be constant. Okay. Now, if we translate what that means that the velocity of our mass is going to be 0 at the times when it's furthest along, because of the elasticity of the band, or if we're looking at it, well, that band's being compressed as well, is at its limits here and here. And so again, at those moments, the rate of change is going to be 0, which means the velocity is going to be 0. So what that means for us is that we need to find the times, and there's going to be several of them. There's going to be times here and times here. That didn't turn out right. So basically there's two different times. Each time this thing vibrates up and down here, so it's T1 and T2, where as it does it, it's going to stop. And so for us to figure out how far the mass is from the equilibrium position, we need to be able to know what these times are. Okay. Now for this question, we don't have to find all the times. We just need one time. And if we know one time in which that actually happens, then we could use that time, plug it into our position function, and then we'll find out how far that particular mass is from equilibrium at that particular time. And again, we're assuming that the mass is going to be vibrating back and forth. There's not going to and we're assuming that's basically going to be in a vacuum. So there's not going to be anything stopping it from like dying down or anything like that. So we're not taking those things into account. All right, so with that being said, we kind of know what we need to do here. So if you remember, our velocity function was minus 2 sine t plus 3 cosine t. And we essentially just want to find out when this is equal to 0. Okay. Well, if we just look at this portion of the equation, then that tells us that 3 cosine of t equals 2 sine of t. And if we wanted to rearrange that, that would be 3 over 2 is equal to sine of t over cosine of t, which is essentially tangent of t. So we need to solve this particular equation for values of t. And of course, we only need one. So in general here, if we have 3 over 2, which is a positive value, sine of t, and I wanted to use tangent inverse here. Notice that here I can actually do the tangent inverse like this, and I will actually get a correct answer, okay, if I just wanted to look at one of those times here. Now, in general, these are going to be all of the times that this particular mass here actually stops, okay? So basically the times when it's going to be the furthest from equilibrium. And so we know this where n is going to be some integer here. We know this because the period length of a basic tangent function is pi units. And so all we're saying is that, hey, this is going to happen once every pi units, or approximately, to put it in context of this problem, about one time every 3.14 milliseconds. Okay. And so here, remember again that we are considering when t is greater than or equal to 0. So here I can say when n is equal to 0, then that means that t is just tangent inverse of 3 over 2. And since these numbers are positive here, I know that that translates to, and I'll go back to the graph here. What happened? Don't know what happened there. Let's try that. Okay, got that together here. So let's go back to this graph. So if you look here, notice that our tangent inverse function here has positive values, meaning positive t values or positive angles whenever the values that we plug into it for, and this I'm calling it y, but we could say it's x here. Whenever those values here are positive. So positive values here yield positive outputs for the tangent inverse function. Negative values here yield negative values for the tangent inverse function. Okay. So this is how we know that we're actually looking at this and we are properly using the tangent inverse function here. And so now all we need to do is figure out what tan inverse of 3 over 2 is. I'll come here, calculate that. This is tan inverse of 3 divided by 2. And that's about 0.98 milliseconds. Okay. So we see here that just under 1 millisecond when that happens. I don't know why this space is out so far, but so 0.98 milliseconds. All right. So now we know at what time, roughly, or at least one of those times, for which our position of our mass here is going to be the furthest from equilibrium. So now what we can do is we can take what we have here and actually use it. So we can say the position at a maximum of t is just going to be the position at tan inverse of 3 over 2. And of course, that's roughly 0.98 milliseconds. So we'll come back here and actually just use this function here for that. And so our original function was 2 cosine, and I'm just going to use the answer that we got from last time here, and then plus 3 sine of the same answer. And we get about 3.6 centimeters, because remember, we're measuring everything in centimeters here. Okay. All right, so roughly about 3.6 centimeters. So this is the answer that we want to this question. All right, so for our next question, we're asked, when is the speed of this mass that's bouncing up and down going to be the greatest? Okay. So if we take our scenario again, we have a mass that's bouncing up and down, up and down, up and down. We already know that the rate of change of the function is going to be 0 at these extremes. Okay. We already know that, and we're assuming that this is equilibrium here. Now, notice that whenever our mass is at these extremes here, it is not moving. And so in physics terms, we know that things that are moving versus not moving either have a lot of potential energy or a lot of kinetic energy. And so at the moments where we are at the extremes here of the system, we know that the mass has 100% potential energy, 0% kinetic energy. Okay. And of course, the same thing happens down here. Now, as this mass goes from this extreme and tries to get back to equilibrium, the shift in potential energy to kinetic energy starts to change. And so the more this moves, the less the less potential energy we have, the more kinetic energy we have. And it turns out here that right when it passes through equilibrium will be when we will have 100% kinetic energy and 0% potential energy. So this question here asking when is the speed of the mass the greatest, well, V of t is going to be maximized at the same place where it passes through the equilibrium. Okay. And so we know, I was going to write it one way, but I think I'm going to write it another. This will make it a little bit more simple. So essentially, V of t is maximized when S of t is equal to 0. And this is another way of saying the times at which our mass are at equilibrium. Okay. Now, if you remember, we've actually already found this. Okay. And we found it for the first time it passed through the equilibrium. And so here, for the first time, if you remember, we had something that was roughly like 2.55 milliseconds. Okay. I'll just keep it as ms here. But also notice that with this, we know that since this is bouncing back and forth and we don't have anything that's going to die down that particular action here, we know that every pi, every integer multiple of pi, if we add this to an integer multiple of pi, that's another time that it's going to happen. Okay, and so this will be integer multiple of pi, and I'm going to rewrite pi, and this is just for simplicity here. I'm going to write it as approximately 3.14. Okay, and of course n is an integer. So in approximate terms, we're going to have the speed of the mass be the greatest every time it goes through here, meaning that the first time is going to be 2.55 milliseconds, and then every 3.14 milliseconds after that, that's when the mass is going to be the greatest again. Okay. Now, of course, if I was doing this in exact terms, I would have to write it like this. So this is exactly all of the times when our mass will pass through equilibrium, or said differently, it will be all the times in which the speed of the mass will be the greatest. All right. So I hope that this particular problem kind of gives you an idea of how we actually use these derivatives to be able to solve application problems like this, like a spring mass problem. Spring mass problems show up a lot in mathematics, especially in calculus courses, just because it's used to model so many things, anything that vibrates, or anything that kind of has like a cyclical motion to it, can be modeled by a spring mass system. So this was a very, very, very simple example of that. So I hope that this video helped you to be able to understand how to look at these things a little bit more. And I hope that the video series also helped you to be able to understand how we use differentiation rules to be able to take derivatives of functions and use them in applications. Take care.